Today we're going to look at piecewise defined functions. Now, piecewise defined functions are important because sometimes a single formula cannot be used to describe a function on its entire domain. In other words, sometimes the domain has to be broken up into pieces on which separate formulas are used. This can happen in a variety of situations. And so it's a useful concept to understand and to understand the terminology and notation behind these piecewise defined functions. So you'll recall that in general, a function is just an assignment. It's an assignment that takes an input and assigns to that input a unique output. So for example, let's go back to the birthday example. Every person in a classroom has one single birthday. Therefore, the birthday is a function of the person. The person is the input, and the birthday is the output. No person has more than one birthday, which is what makes it a function. If one person was born on 2 different days, which is not possible, then it would not be a function. 2 people can share the same birthday, maybe even 3 people. Maybe 3 people in a classroom were all born on September 7th. Well, those 3 people have the birthday of September 7th. It's still a function because no one person has more than one birthday. The birthdays, in other words, the outputs can be used more than once. So 3 people can be born on September 7th, but each input, each person, can only be assigned to one output. Same thing with Social Security number. Every person has a unique Social Security number. So the person is a function of the Social Security number, or getting ahead. The Social Security number is a function of the person, right? The person is the input, the Social Security number is the output. Now that relationship is unique both ways. In other words, if you know somebody's Social Security number and you have access to the Social Security database, you can figure out who that belongs to. So the function is something called an invertible, and we'll talk more about that as we progress. But basically the output is also uniquely matched to the input, meaning the function can go back and forth both ways. So we'll get into that later. But for now, let's just do a quick graph of what a piecewise defined function might look like. So we have a y-axis and an x-axis like this. And we have some function. Maybe here it looks like that. And then there's a sharp corner like that. And then maybe it does something like this and levels off. So you can see let's make this like that. So we can see 3 separate types of behavior. One, we have this sort of curve and it's going up, and then suddenly it stops going up and starts going down at a nice linear rate. And then at this point, it stops going down and then it starts to curve up and eventually levels off at this horizontal asymptote. In other words, it levels off like a straight line as you move to infinity. So let's define these points. So let's call this the point A. This is the point B. And of course, this is the origin. So on the interval from 0 to A, we have one function, behavior. In fact, there might even be a specific equation that models this. We can call this, let's call this one f1 of x. So on the interval from 0 to A, this function can be described by a particular formula given by f1 of x. On the interval from A to B, we might have a different actual function, so a different equation that describes this behavior. That now it's a linear function and it does something completely different than what it was doing on the interval from A to B. And then finally, on the third interval from B to, let's say, infinity, we have an f3 of x. So it's a new behavior again on this third interval. All sorts of systems can have this sort of, where it's one formula on this piece, different formula on that piece, a different formula over there. In business, you can have startup costs where you might have a flat rate, and then once you break some sort of threshold, you have some sort of curve. If you're selling tickets for a theatrical production and you're looking at your revenue or your profit from the event, in your theater has a certain seating capacity. There might only be 300 seats in the theater. So as you increase the ticket price, your revenue grows up linearly. Well, the revenue increases, as you sell tickets because you're filling up to the capacity. Beyond the capacity, you can increase the ticket price, and then you get a different sort of behavior. So let me not go into that. We'll see an example like that later in chapter 4, but let me not get to the details. But you do see some sort of trend where your profit's constant because, let's just think about it like this. Your ticket price, P, and then your profit on this axis, I'll just call that Y for now. So you have constant profit because if you sell the tickets for less than some threshold, well, let's call it the revenue, not the profit. Just think about sales revenue from ticket sales. So if you're up to this value right here, your revenue's fixed, and that's because if you set the ticket price anything less than this minimum or this amount right here, maybe $100 for example, it's going to be sold out, right? So if you sell it for $90, it will also be sold out. Well, if it's sold out at $90 and you give the tickets away for $5, of course it's also going to be sold out. So up until this point right here, the theater is just completely sold out. Once you start increasing the ticket price here, maybe fewer people start to purchase it. And then, of course, as you increase the ticket price more and more, fewer and fewer people will purchase the ticket. So you then get some sort of downward trend because, well, actually, it's a little bit, well, maybe for the number of tickets. Let's change this to number. So this is how mathematicians think. You come up with an idea, you see where it takes you, and then you say, oh, maybe it's like that. Never be afraid of that sort of kind of scattered approach to problem solving. Oftentimes with videos like these, you might, suspect that, the math gods out there just immediately know how to solve problems. Nothing of the sort. It's like you play with the ideas, you formulate them as you go. Never be afraid to do that on your own. And oftentimes, even when problems that might appear clear cut, you have to take an approach where just start doing anything. Do something for a little while, work on it, let it, think about it, let the problem sit on your mind. You get more ideas as you progress, and you say, oh wait, this is a better idea to go back and do that. So this is just the number of tickets sold. It's simple as case. Obviously it's fixed if we're less than, let's say, $120. If it's $120, it's sold out. So any price less than $120, it's also going to be sold out. So this would be like 300 seats in the theater. And then as you increase the price above 120, fewer people purchase the ticket because, it's like, okay, maybe at 125, you're only going to have 295 people buy tickets, right? So fewer people are buying tickets now because you're outpricing it. So you get this steady decline in the number of tickets sold. But as the number of tickets being sold is declining, the ticket price is increasing, so the revenue at this point might be going up. So the revenue will be going up, and then of course it's going to have to come down again because eventually you have 0 people in the audience. 0 people buying tickets means 0 profit. So initially, you're increasing the ticket price, so you're making more revenue because all 300 people are paying an extra $5, or maybe not all 300 people, but all 299 people now are paying an extra $5. So you're losing one ticket sale worth $300, but you're gaining 299 people, each paying an extra $5. So why set your price where it sells out? Because if you sell it higher, you can make a little bit more in revenue. You increase it again, revenue is going to go up. So what's the optimal ticket price in order to increase your profits? So again, I mentioned earlier, this is going to be something we'll look at in detail in chapter 4, but it gives you an idea where, okay, well, up to this threshold, you have one behavior. After this threshold, you have another behavior. In terms of the revenue graph will look like something like this. It will increase linearly because it's just proportional to the ticket price, right? Because it's a full house, whether it's $0 or $1. So this is maybe $300 in revenue, $600 in revenue, $900 in revenue. Right? Every dollar increase of the ticket price, you get an extra $300 of revenue because it's sold out. And then we get some sort of quadratic or some sort of thing like this. So the idea is, okay, well, where do we have the maximum revenue? Where are we generating? What ticket price should we set to generate the maximum revenue for the show? That's just one, simple example, but you can see how you might have one behavior on one part of the interval and a completely different behavior on a different part of the interval of your domain, right? So that's an example of that. Another example might be friction. When you have an airplane landing and the landing gear, when it first touches down, the wheel's not rolling yet, so you get a kind of a sharp increase, a discontinuous increase in the frictional forces, and that's what creates a little bit of smoke when the wheels touch down. It's the friction. But then very quickly the wheel starts rolling, and then the friction force suddenly changed because you have rolling, so it's now rolling without slipping. But for a very brief period of time when the airplane first touches down, the wheel just drags before it starts to roll because it's just, the wheel's not rotating, and then it suddenly hits the pavement, and there's going to be a big friction force, and then it's going to start to roll with the pavement. So you get, zero friction, this huge amount of friction, and then back down to just rolling. So probably, no friction because it's just rolling without slipping. If there's a little bit of slippage, there might be a little bit of friction in there. So again, very, discontinuous jumps in the function behavior. One behavior before it touches down, another behavior when the wheel hits the runway, and before it starts to actually roll, while it just kind of drags for maybe even a fraction of a second, and then a different type of behavior for the function after the wheel starts to roll. So you can imagine all sorts of situations on your own. Try to come up with a few, do a brainstorming, say, what sorts of, experiences have I had or witnessed in real life where, some sort of functional relationship is described by this, and then suddenly it's described by some other behavior like that. They're pretty common. So how do we actually represent this mathematically? We have three different functions. And functions, of course, can be described by words, data, so tables of data, pictures, and formulas. So let's say that we have a formula for all three of these functions. We have a specific formula for f1 of x, specific formula for f2 of x, a specific formula for f3 of x. How do we write one formula for the whole thing without being so let me see, select, let me make some space here. Aha. Let's go back to the pen. Let's do black. Okay, so this is how we write. F of x is equal to, nice big curly bracket, because we're going to stack up all the functions on the right of the bracket. So it's like the brackets gives you all the instructions for how to compute f of x. So first we have f1 of x, which is one specific equation. Then we say for x in 0 to a. So whenever the variable x is in that first interval from 0 to a, we get one equation, f1 of x. f2 of x for x in the interval from a to b. So x in a to b means that x is, since it's a closed brackets and not rounded parentheses, it includes the endpoint. So I'll talk about the endpoints later, but this includes the point a and b. So actually, to be safe, let's say open. So that way, at the point x is equal to a, we're going to use this definition because a is included in this interval because it's the square bracket that includes the point a. Here, it's an open bracket for a, meaning the second interval is, open bracket, all the points in between, and then close. So that's the second interval. That's the interval a comma b, like that. So not including a itself, but anything slightly greater than a is included, and all the way up to b. So we use the function f2 for that second interval. f3 of x is for x in open bracket b to infinity. Infinity always comes with an open bracket because you can't actually be at infinity. Infinity is not a number. It's a symbol, but not a number. So infinity is just an idea that represents everything as large as you want to go. So b and up. So we don't want to include infinity in our set notation here. And this is equivalent, the first one is equivalent to saying 0 less than or equal to x less than or equal to a. The second interval is equivalent to saying a less than x less than or equal to b. And the third one's equivalent to saying x greater than b. So this one belonging right here, the second one belonging in second one, third one. So they match up like that. So it's just alternative notation. But you can kind of see how this is set up notationally for this piece. So this is called a piecewise defined function. Right. So basically, when you're reading a piecewise defined function, let's say you're given some piecewise defined function and you're asked to compute f of 13. Okay, your first task is to say, okay, all these different pieces, where does the point 13 lie? So first thing you do is you want to go over to this part, because this basically gives you your instructions. If x is on this part of the domain, then use that formula right there. If x is on this part of the domain, use this formula. So the first thing, if you have a piecewise defined function with a formula set up like this, is to say, okay, f is equal to x is equal to 13. Well, where is the point x is equal to 13? Which piece of the domain, so which interval, defining interval of the domain, is the point x is equal to 13 on? So if 13 lies between a and b, for example, okay, then we're going to use f2 of x. So then f2 of x will be the formula that we plug x is equal to 13 into to get the output for this function right here. So let's do a simple example. In fact, let's do a simple example of a piecewise linear function. 5, 1, 2, 3, 4, 5. That should be good enough. Let's go from 0, 0 to 2, 2. Just like that. Let's make it blue. Okay. Kind of a thick line, but you get the point. Okay, so that's F1. So this first one, let's annotate with green. This first one is going to just be y is equal to x. Right? Slope is 1, passes through the origin, y is equal to x. Okay, now let's do from this point to this point right here. So okay, so here's how you can think about linear functions. You know, there's the formulas, there's the point slope, slope intercept, all that stuff. But it's always good to just have a hand, on the ground feel for this. So just say, okay, look at what you have first. Okay, it's passing through this and this. This is the point 2, 2, and this is the point 4, 1. So first thing is, okay, well, what's the slope? So let's draw some lines. Okay, the slope, we're going down by 1. So on this line segment, we're moving down by 1, and then as we move to the right, we're moving to the right by 2. So 2 to the right, down 1. It's a downward slope, so the slope is negative, and it's just going to be a 1 to 2 ratio, right? Because we're moving down 1 in y as we move across 2 in x, so it's 1/2. So the slope is equal to minus 1/2. And this is easy enough. Every 2 units we're moving in x, we're moving down 1 in y. So where's the y-intercept? Well, if this is at a height of 2, this line would continue to a height of 3 right here. So that second section is going to be y is equal to 3 minus 1/2 x. Right? Now, if you did the point slope, okay, you can use the point 2, 2. So you can say, well, y minus 2 is equal to minus 1/2 times x minus 2. Right? So you get the slope, and of course you can also calculate the slope by just saying y2 minus y1 over x2 minus x1. So that y2 is 1 minus 2 over 4 minus 2, which is minus 1/2. And then your point slope formula, you can distribute the minus 1/2, so you get minus 1/2 x plus 1. This is y minus 2. So y is equal to 2 plus 1 is 3 minus 1/2 x. So you can do some work to do the same thing, but you saw how I did it earlier. I just kind of visualized it. I said, okay, so I move over to the right by 2, I'm moving down by 1, that's 1/2, and it's downward, it's negative. Okay, it's 2 to 1, and hey, I started at the point x is equal to 2, so I'll also drop 1 unit when I go from 0 to 2, so the y-intercept of this line segment, if we were to continue it, is just at 3. So we get y is equal to 3 minus 1/2 x. And then let's say we go from the point 4, 1 to the point 5, 2. Okay, now it's kind of the opposite. It's flipped. It's going up instead of down, and the slope is 2 instead of 1/2, right? Because as we move to the right by 1, we're going up by 2. So the slope is 2. So this line segment, the slope is 2. For this one. And we're at 4, 1. So okay, well, let's just think about how much we would go up going from 0 to 4. 0, 1, 2, 3, 4, slope is 2, we'll move up in y by 8, right? Because if we're moving over 4 in y, or 4 in x, and for every x increment, the y increases by 2, 2 times 4 is 8, we're going to move up by 8. So 8, and we're at 1 at this point, so we're going to be at negative 7. So for the third one, it's y is equal to minus 7 plus 2x. So the whole thing together is going to be given by f of x. So the first rule is just x, and this is for x is on 0 to 2. And the second rule is 3 minus x over 2 for x is in 2 to 4. And then the third rule is minus 7 plus 2x for x is in 4 to 5. Now also we'll note that this is a continuous function, so I can draw the entire function without lifting my pencil, right? So it's a continuous piecewise defined function. So when it's continuous like this, it's really okay, whether I want to make this the open interval and include x is equal to 2 in this definition or in that definition. It doesn't matter where I put the point 2. Same thing with x is equal to 4. It doesn't matter if I put it here, in this second one, or in the third one, because if you plug in 4 for the second one, or if you plug in 4 for the third one, you get the same output. You can check. 4 over 2 is 2. 3 minus 2 is 1. 4 times 2 is 8. 8 minus 7 is 1. So it's the same output because both of these definitions intersect at that point where they change over. Now, if they didn't do that, so if you, instead of having a piecewise function like that, if you had something like this, you have to pay attention to which rule. So here, this point here belongs to the second function, and this point here belongs to the second function. It's not included in the first and the third. So here it matters whether you make which one an open or a closed interval on which side. So just make sure to pay attention for that. So if it's continuous, put it wherever you want. Doesn't matter. But if there's a jump like this, then it's going to be, f1, the first function for, let's say, 0 to a, open endpoint at a, f2 for a to b closed interval because these endpoints are included in the second definition, and then f3 from b out to infinity, not including the point b. So this is an example of how we took a piecewise defined function we had the graph, and we came up with the equations. We come up with the equation for each subinterval, so that is for each piece, and then we plug them together like this. For the specific case where each defining function on the subintervals is a linear function, so we see this is a linear function, this is a linear function, this is a linear function. In other words, for piecewise functions that, even if we have a jump in it, it's okay. Some more jumps. Piecewise functions like that, where each segment is a line segment, so each segment of the function is linear. We call that, that has a special name. It's probably what you would have guessed, piecewise linear. So that's a piecewise linear function. If you have but you can have piecewise functions in general. You can have, any sort of behavior, a sine wave, and then it switches to a linear function, and it switches to an exponential function. So it could be anything that in general is called piecewise defined function. This is a piecewise linear function. So that's kind of an overview of piecewise defined functions and their importance. So a little indication of their significance and a few kind of conceptual examples. We didn't really work out the details of those, but you can see why piecewise defined functions are important and why they show up.